behind schedule, but luckily I think my talk will be relatively short because I don't think we may have you do some examples, but maybe not, just depending on how the timing goes. So I'm going to talk about advanced data objects in YT. In the background, you can see a movie of one I made a while ago, and I'll show you how to make this in a few more slides. So we're going to look at the standard data containers. Oh, it's a movie, and it shows the green shaded area is the inside of a data container. So stuff, if this is your volume, the stuff inside the green is where you'd be pulling data from, and then the stuff that's not green is excluded. So basically, yeah, a volume rendering a once field. So this is not real data. This is very synthesized. So we'll be covering standard data containers, the Boolean data containers, which allows you to mix data containers together. That's how I made that thing on the first slide. Covering grids, fixed resolution buffers. We'll go over the FRBs relatively quickly because we've seen them a couple times. And then ray objects and clump objects, we'll just look at them briefly. Britton's going to talk in much more detail about clump finding, but I'm just going to point out a couple things about the clump objects themselves. So the standard containers that we've all seen are the sphere, the parallel pipette region, and the disk. And here's a volume rendering of the three. Where you've seen all these before, but these are the standard containers in YT. And so one thing you can do with containers that's very useful is you can save them for later. So if you define one, or you figure one out that's useful, you can save it with the save object command. And then later, in the same script or in a different script, you can pull it out. You have a question? Oh, and later you can pull it out. They're saved under string names, so it's basically like how you might say something in a dict. And then you can use objects again if it was something you need to remember. What's that? It uses YT's built-in pickling because when you save a data object, you have to save a lot more things than just what pickle would save. But it's essentially built on top of pickling. So just for you, those of you who didn't hear, you can hopefully, most of the time, we hope you can upgrade YT. And if that breaks in the future, we'll let you know. So what are Boolean data containers? These are containers that are built by relating already defined data containers. And they are related using the standard Boolean relations of and, not, and or. And you can have nested logic. And once you've defined it, it works like any other container. So you can use quantities on it. You can save it to the hierarchy like I showed you in the last slide. You can pull particles and things out of it. So let's take a look at the OR command. I've defined two spheres here that are non-overlapping. And I've made a Boolean region called bool that says sphere 1 or sphere 2. And so what this says is if I have a point in space, that point in space is in the new container if it's inside either the first sphere or the second sphere. So you get something like this with two spheres, disjoint, and the data you pulled out with the Boolean container could come from either one. Not, on the other hand, so here I'm defining two regions, and I'm combining them with the not command. Not, the best way to think about that is it's a subtraction where the second region is subtracted from the first. And so if I show you the movie, you can see that I have a large cubical region where I pulled out a corner by using the not command. The and command can be thought of as the overlap. So I have a region and a sphere, and the combined region will be where they overlap. So I have basically the corner of the region and then part of the sphere, and so I have this sort of four-sided shape. And then finally, you can use nested logic to do more complicated volumes. Here I've defined a couple spheres and a couple regions, and I'm relating them with ands and nots and parentheses. And you'll see that I have parentheses as our string, and I have an open and closed parentheses. You can't forget both of them. And this is what we saw on the first slide, where I have a large region where I've subtracted out the sort of the four-sided sphere corner thing we had earlier, and then I have the final sphere as sphere 2, which, because of the periodic boundary conditions, is actually subtracting off from multiple places around the initial big box. So now you might be asking yourself, well, what is this good for? I mean, great, I can make these fun movies, I can make these weird shapes that aren't really physical, but I'm going to show you some examples of things you might want to do with a Boolean container. In this script, we started out by finding halos. We haven't discussed really finding halos here, but in YT, finding halos on a data set is just as simple as what I've highlighted. So line 3, I find the halos in my data set. Right here, what I've done, oh, by the way, you can take a look at this script for yourself. It's 2082. But I don't think we should run it right now unless you really want to, because we're a little behind time. It's okay. These next two lines, what I've done is I've gone to the halos and I'm pulling out the first halo. Like everything in YT, halos are objects. So H0 represents the largest halo in the box. Line 5, I'm actually making a sphere data container that's the size, the physical extent of the biggest halo. And then line 6, I'm calculating the angular momentum of the matter inside that sphere. And then line 7 and 8, of course 7 and 8 is one command. I'm defining a disk container that's aligned along the angular momentum vector of the halo, that's the size, that's smaller than the maximum size of the halo. So its radius is about the 10th of the halo, which you might say, well, that's about the size of the galaxy inside the dark matter halo. And I'm giving it, about the thickness, 10 kiloparsecs, around the size of a large disk galaxy. And then this command here on line 9 is creating a Boolean region that is the sphere minus the disk. So this is the stuff that's outside of the disk galaxy. Right here on line 10, on the outer part, the stuff that's outside the disk galaxy, I'm selecting the particle. First of all, line 10, I'm finding the particle type for everything that's outside the disk. And then 11 and 12, I'm actually adding up the mass of particles that are dark matter, which in Enzo is type 1. And then in line 12, I'm adding up all the mass. And in line 13, I'm basically finding how much matter outside the disk galaxy is dark matter, which you see is quite high. It's over 90%, which was what we should expect. I mean, of course, if, like most of the galaxy should be around, 80%. But since we see, the outer part of the galaxy is usually dark matter rich, it's higher than the cosmic mean, which is what we should expect. Are there any questions about this? Okay. Another thing we might do with galaxies is analyze all the halos at once, which is what we're going to do with this script. Oh, so there we go. I forgot I had an extra slide there. So first, again, we find all the halos with one line. These lines, I make a list called spheres. And then lines 5 through 7, I'm actually creating the list of strings and data containers that will be used to make the Boolean region. This if statement here on line 7 basically just makes it so that I don't have a trailing or when I build the list, because I don't need the begins and ends with data containers. Line 8, I actually make a Boolean container that's got the spheres for all the halos. So that one of those first movies I showed you with the 2 spheres rotating, line 8 would make, 1,000 or 800 or whatever many halos there are. There's that many spheres now inside my volume. Line 9, I make a data container that's the whole box. And then line 10, I'm actually subtracting out the full box and I'm taking out these spheres. So now I've made a new data container that only covers where halos are not. And then lines 11 and 12, and because I wanted things readable, these are actually not new lines down here. They're just, I wrapped them around so that so it fit. I'm finding out what the average temperature is inside and outside all the halos. And as you see, inside the halos, the temperature is much higher than it is outside the halos, which is what you'd expect. But the thing is, I think we've done this all in 13 lines, and these quantities are done in parallel. Halo finding is done in parallel. So this script that's done in 13 lines, you could parallelize without changing anything. It would run faster. And I think you can do some fun things that don't really make any sense with Boolean containers, but you can also do some things with them that are really powerful and make things a lot simpler. So now to change gears completely. Are there any more questions about Boolean containers? Covering grids are kind of like fixed resolution buffers, but they don't do any interpolation except for the smooth. And the covering grid must have the same cell size to the level at which you're extracting. So if we have a root grid here with 2 levels of 6 by 6, and we want to extract down to the second level, the covering grid, the cells in the covering grid must have the same size as the level in the original grid. So it's not like the fixed resolution buffer where you can pick any size. They have to have the same size. And here's an example of how to do a non-smooth covering grid, where you've defined a cube where you specify the level at which you wish to extract, a left edge, and a dimensions. And once you've defined the covering grid, you can pull out quantities like you can with any other data container. I've pulled out density here. And then what I've done in lines 7 and 8 is I've actually flattened this cube into 2 dimensions. It comes out 3 dimensions at line 6. 7, I'm flattening it down to 2 dimensions. And then line 8, I'm actually saving this flattened cube to an image. Here's how the only difference between a non-smooth and a smooth covering grid looks. You just add the word smooth. And to see what's different, here's what you would get if you ran on the data set I referenced. At this resolution, it's not clear what the difference is, but I'm going to zoom in on a corner. And if you look, especially at the filament regions and things like that, the non-smooth is blocky because there's no smoothing done. It just pulls the data raw. But on the smooth, you can see that the blocks have been smoothed out, just like you'd expect. Yes? Oh, yes. Because In Enzo, which is what YT is based on for most, 0, yes. Question? It's only going as deep as you specify, and it's doing a trilinear smoothing. So no, it's not using anything deeper than you specify. So we've already seen fixed resolution buffers. As I just said, they can be whatever dimension because it's done using pixelization. We've already seen how to save fixed resolution buffers as fits. But I just noticed on my script at line 6, my fixed resolution buffer is size 987, which is not a factor of really much, but it works just fine. Here's a slice of temperature in the fixed resolution buffer. Here I'm using a projection to a fixed resolution buffer, and then here's the output. Are there any questions about that? Of course, we've seen it already. A new object we haven't seen before that can be very useful are ray objects. These are defined by a start and end point, and they provide values from the cells along the path of the ray. One thing to remember is because rays can go through regions of different refinement, you have to actually think about how you're using the ray, because rays come with them two new variables that don't exist in other data containers, lowercase t and lowercase dt. T is the normalized position length along the length of the ray. So t, the first value of t would be at the beginning of the ray, and the last value of t would be the end of the ray, and the last value of t is maybe not necessarily 1, but it's normalized to 1. And dt gives you the normalized space between the points along the ray in the cells. So to give you an idea of how this works, here's a script that I put together that works on the sloshing data set. So on line 5, yes, I define unitary, and on line 6 and 7, I define my start and end. Since this data set 0 is in the middle, the values to the left of 0 are on the left and above 0 on the right. And then on line 8, I define my ray. And then line 9, I do like any other data container. I pull out temperature from the data container. And then continuing on with the script, to calculate the length of the ray in actual physical units, I use this function that you might have noticed I imported in the top of the script on line 2. I calculate the physical length of the array, on the ray rather. Line 11, I pull out this t value I mentioned before, which gives you the distance along the ray in normalized units. And then the rest of the lines, I'm actually making a figure from the temperature data that I just pulled out. Figure 12 makes the figure, 13 makes the patch that I'm going to plot on top of. We haven't seen this add subplot command before. This is a matplotlib thing. And then on line 14 is where I'm making the line plot. And you'll notice I'm multiplying t, which is the normalized length, times the actual length of the array. And then I'm also plotting capital T, which is the temperature. And then I'm setting my axes label, and then I'm saving. And I get this. So I have physical temperature in Kelvin, and I have physical distance in centimeters. And this is what the temperature looked like on that ray through the sloshing data set. Any questions about rays? That's correct. That's why you need to use the t and the dt. depending on your needs. So clump objects are actually extracted regions. They work like normal day containers for fields, but in general they do not work for particles. This is something that someone out there who's looking to get into YT could fix. I will show you an example of what I mean by how it's broken coming up. Just like I said, Britton will cover this in more detail, but this script I'm setting up clump finding in a sphere. So on line 3, I find the densest point in my simulation. On line 4, I make a sphere around it. Then lines 5 and 6, I find the range of densities inside that sphere, but I set them to even values of 10, which is what I'm doing with the floor command. Lines 7 and 8 introduce something new that I don't think we've seen before here. You can actually shortcut to the analysis modules in YT without doing a from yt.analysis modules import command. You can actually go straight to them with this amods shortcut. So that's just another way to get to analysis module without doing an import. So I thought it was good to show that here. So then on line 7, we're actually defining our first clump, which may not actually be a gravitationally bound clump, which is something, again, Britton will say. And then on line 8 and 9, we actually go ahead and run the clump finder. No, but there's more scripts, see 1 and 2. Yeah, there's more to come. And then on 10 and 11, I'm actually taking these clumps I just found and turning them to basically a list. So sorted is a list of clumps. And actually, I regret using the word sorted because sorted is actually a keyword in Python. So you probably don't want to use the word sorted because then it'll mess up other stuff in Python. And then lines 12 through 17, I'm making a projection in a plot collection of the region around my sphere that I just produced. And then on line 14, I'm doing a modify, a callback of the clumps. And so in this next picture, you can see where it's found the clump. The largest line is actually the initial clump I found, the initial sphere. And of course, because of AMR, it's not an actual sphere because of the cell sizes. But then it found a clump inside the big clump. As you can see, it's around the center of this halo. So that can be very useful to see where your clumps are. But as I was saying in an earlier slide, clumps can be, in many ways, acted on like other data containers. You can pull fields out. So what I'm doing on lines 18 and 19 is I'm iterating over the clumps that I found, and I'm looking at how many cells are in them, which is what the X parameter does. It gives me the cell center. But then on lines 20 through 23, I'm again iterating through the clumps, and I'm looking at how many particles are in the clump. And if you were to run this, you would, first of all, see that my two clumps, my small clump has 529 cells, the bigger one has 11,000 cells. But then when I try to look at the particles, I get this warning that returning particles from an extracted region could be incorrect, and in fact, I get a trace back and things crash. So clumps aren't fully featured data objects. Matt?
But you can, any particle field that has been deposited can be accessed. Like if you do the CIC deposit of particle mass, you get that, which isn't quite the same.
No.
But it will get you something.
But like I said, that's a place that we would love someone to step in and fix, because most of it's there already. You'd have to learn some of YT, but you wouldn't be doing something from scratch. And if this is something that's important to you, to pull the particles out of clumps, That would be a great way to add to the cause. Are there any questions? Yes? I think so, yes. No, yes, you can. Yes. So the question was, can I use clumps with Boolean containers? And I think the answer is yes. Yes. So you should be able to make Boolean containers of clumps.
And if anybody wants to put particles into clumps, there is a clear way to do it. But it's hard.
The question? I was using Redshift 6 from the Enzo 64. Yeah. Yeah, his whole talk is on clumps, so I didn't want to steal his thunder. Because he's all about thunder. Okay. Well, thank you.